Welcome to the 7th tutorial of the RISC-V architecture and assembly language series. The earlier tutorials covered most of the common RISC-V assembly instructions that are needed to build many practical applications. Going forward, the emphasis will be on more advanced topics instead of merely describing the syntax and usage of the lesser used instructions. This is more in line with professional programming. This section will show how we can combine RISC-V assembly code with the C programming language. Although many embedded application programmers may sometimes have to resort to development using pure machine code or basic assembly, we've seen that more often we have the benefit of development under the Linux operating system environment, giving us a wealth of tools to aid our task. We have seen the advantages of using system calls, especially in the area of screen output and keyboard input. This has been best illustrated for those using real hardware, such as the platforms described earlier rather than emulation or simulation. An operating system such as Linux allows us to use C code, which can be compiled with RISC-V assembly instructions. Note there is a prerequisite of having a basic understanding of C programming for this tutorial. Prior to combining C and assembly together, we will spend some time within the C environment, writing simple code and compiling. None of the C code presented here is overly complex, and there is a wealth of online tutorials to be consumed that will cover the basics for what is needed here. As an aside, an alternative to the GNU compiler collection which is known as GCC is Clang, which can be installed under Ubuntu-derived Linux systems by the command sudo apt install -y clang. Enter the C code shown, and then compile it with GCC. Run it to observe the output. Compile the code this time with GCC-S to retain the generated assembly files. Normally, the intermediate files are deleted once the compilation is completed. The assembly code that was generated by the compiler is shown in two distinct columns for clarity. If you followed the tutorials in sequence, then it should be easy to reconcile some of the assembly instructions with the C source in the generated assembly file. The stack pointer has been set up with the instruction add immediate SP-32. This was covered in tutorial 6. You can see how the variables first and second are assigned in the highlighted instructions. Load immediate to T510 and load immediate to T520. In between and after the load immediate instructions, there was a stack push to save register A5. A copy of register A5 is loaded into register A4 via the move instruction. Both registers are added together using addword A5 A4 A5, and the result is stored on the stack. Following this, the output print parameters are set up by the argument registers A0, A1, and A2. The table shows the main levels of code optimization that the compiler can generate. The assembly code that was generated by the compiler used the default optimization level. Generally, optimization level 2 is considered a good compromise. Level 3 can use inline code similar to what we have seen with macros, but it can gain this optimization at the expense of size. If the file has been compiled with the -G option, then the optimization level may be included in the final executable. Under Linux, the grep utility can be used for this with the -A switch denoting that the file is an executable. The extract shows that the optimization level used with this binary is 3. It is recommended to stay with the default level of optimization until the testing and debugging phases have been carried out. The assembly code for the add program listing is smaller than the code generated with default optimization. Here with optimization level 3, the compiler pre-calculates the addition. And since the values of the variables first and second are constant and do not change, it eliminates the add word instruction. In addition to the change, the stack handling has been reduced. It is important to note that the optimized code may be harder to debug since it has performed optimization that may be more difficult to spot, since for some of the instructions there is no longer a one-to-one correspondence. These optimization techniques are known as constant folding and copy propagation. Constant folding occurred here by evaluating 10 plus 20. And just using a single variable to store the result. In the code shown, it was achieved with the instruction load immediate A4, 30. In C, it would simply look like sum equals 30 without using the variables first and second. Constant propagation will replace the variables with their values. So it can replace the value variables first and second with the constants 10 and 20. So instead of a statement like sum equals first plus second, the compiler can substitute sum equals 10 plus 20. Now consider the program listing here. This one uses scanf to ask the user for the integers. An example of the output is shown. So the user is prompted to enter two integers. Scanf will read them in. And here's the output of the program. Now, since the program asked the user for input, the values of the variables first or second are not known until the runtime, then consequently, constant folding and propagation will not apply. Compile time optimization is a static process, unlike runtime optimization, which responds to dynamic conditions. Some of the techniques used in runtime optimization include caching, which remembers the result of a lookup function. And adaptive inlining, which decides which of the functions should be inlined by monitoring the routine's execution frequency. The high-level power of C can be combined with our RISC-V assembly language programs. The assembly language program is assembled into an object file, as usual, but it is linked with the program using GCC instead of the LD link editor. First of all, we're going to generate the assembly program's object file with the AS command, and then we're going to link it with the C program using object file GCC. The C program shows how to call a routine that has been written in RISC-V assembly. So we build the executable GCC. The C variables x and y are passed to the function using the A0 and A1 registers, with the multiplication result passed back through register A0 as described in the RISC-V ABI document. When debugging, you set the initial breakpoint to be main because main in the C program is the starting point. GDB shows the values of the argument registers prior to the get product call in the top screen, and it shows the value of A0 for the return. In the second GDB screen, make sure you use step for tracing rather than next so that you can execute the code one line by line. During compilation, GCC normally generates the final executable binary and deletes any intermediate files. Using "S" generates the assembly file and then halts. However, the temporary files can be retained and studied to see how the generated assembly files look by using the switch. Save-temps. This differs because it carries on doing the compilation. An extract of the generated assembly code is shown here, and you can identify the values 100 and 200. So the C program presented here shows how to call the routine that's been written as RISC-V assembly. The C variables x and y are passed through the function using the A0 and A1 registers, with the result passed through the register A0. This next program uses inline code to execute assembly language instructions from a single C source program. So in this case, the assembly will be written within the confines of the C program. To do this, we use the GNU assembly keyword ASM, and this is used to denote the operands using C syntax. There are two forms of ASM, basic and extended, and we will look at both. Inline assembly is really a bridge that interfaces the high-level convenience of C or even C++ to the low-level functionality of assembly code. First of all, we'll look at basic ASM. Basic ASM is a set of assembly instructions. With inline code, they're introduced by the ASM keyword. Now this is not a C keyword, but it's understood by the compiler. And, in fact, if you're not using the GNU assembler, then perhaps an alternative keyword would be used. Basic ASM is simpler than extended ASM, which we'll look at shortly, and it can be used with no operands. However, this is not the case with C++. So the C program presented here shows an example of basic ASM. The C variables are matching the RISC-V registers T0 through T2. Using the register keyword. The addition is performed with the instruction add T2, T0, T1, included within the ASM block. On entry, it is actually in the text section. After this, the .read-only data section is defined, and then the last part of the ASM block is to return back to the text section. This is important as the program needs to exit from the data section. The printing is performed by the C code. So here we're in the text section by default, then we load up our data in the read-only section, and then we have to return back to the text section. This program is similar, but cleaner as it uses directives to save the section information. At the start of the ASM block, the code is running in the text section. The directive saves the section state and then defines data in the data section. After this, it restores the state back to text. So we use the push section directive, then we introduce the data section. After this, we restore the text section with pop section. Now extended ASM is used to embed assembly instructions directly into the C source. It will reconcile C variables to registers. The template shown uses 0% as the first output operand and 1% and 2% as the input operands. So the multiply instruction multiplies the input operands 1 by 2 and uses 0% as the output result in the operands list. The line equals R means that we are constrained to use a register. The register constraint can be any of the general purpose registers X0 through X31. If you're using memory, then the memory constraints are defined by the letter M. Now if we look at the extended ASM code, the instruction will add the two registers embedded by the operands, %1 and %2. The result sum will be stored in a register. Our number 1, our number 2 includes that these are also in registers. Analysis of the intermediate assembly code shown here that the C variables number 1, number 2 were pushed onto the stack. If tracing the code using GDB, examine the memory showing the values. The GDB command layout ASM shows a more granular display. The cprintf function has been used already. We'll explain it in more detail here. This function is part of the C standard library. It can take a number of arguments. The arguments are handled according to the ABI rules, with registers A0 through A7 providing the first 8 arguments with any remaining arguments pushed onto the stack. Prior to the first printf call, register A0 holds the address of the string that is to be printed. When the function parses the string, it may or may not encounter one or more format specifiers. If it does, it substitutes the value of register A1 into the output string using the format specified. The register index is increment so that register A2 will hold the next remaining specifier, if it is present. It then will resume printing until it reaches the end of the string or another format specifier. If there are more format specifiers than argument registers, they will be passed onto the stack. The more common format specifiers are shown in the table. C programmers are already familiar with these. Performance-critical routines might decide to avoid them as real-time applications might find them too slow, but in general, the benefits outweigh any downside. We can see that using printf or scanf is much simpler than printing with pure assembly. Note that the program is compiled with GCC, which incorporates the C standard library, and this includes printf, as well as many other functions. Building with the -g debugger option, we can just run with GDB. The GDB screen shows the content string pointed to by register A0. Prior to the first printf call, register A0 holds the value hex 2AAAAAA750, which is the address of the string. When it parses the string, it encounters a format specifier, which in the first string is %d. It substitutes the value of register A1 into the output string using the format specified. It resumes printing until it reaches the end of the string. The animated graphic shows an example. A0 holds the address of the string, and we'll pull down each of the contents of the addresses, incrementing as we go until we reach a format specifier. So we're showing the first 11 memory addresses here. And so far, we're just printing plain text. Now we look at the next set of addresses. And here, we've reached a format specifier. So we're going to go to the first argument register where the value is held, and that's register A1. We'll bump up the index pointer so that the next argument register is A2. Printing a space and on to the next set of addresses. So we've met another specifier. From register A2, bump up the index again, so the next value will be in register A3. Printing characters. Print the space character. And here is the last format specifier, which we'll pull down from A3. And that's the end of our tutorial. So hopefully, this will point you in the right direction to program using assembly and C together. Again, the RISC-V ABI specification is key to understanding how arguments are passed and returned. The next tutorial will cover floating point arithmetic. Not only will we cover RISC-V's capabilities, but we will include general information that can be applied to any processor. Again, many thanks for watching. Links to these tutorials and companion PDF books can be found at the website risccomputing.com. See you in tutorial 8.